All right, let's dive into a classic problem from one of the most famous and maybe infamous physics problem books out there, Irodov's Problems in General Physics. This one is a real gem because it looks so simple on the surface, but it's hiding a really beautiful and kind of surprising piece of physics inside.
So here it is, problem 1.157. It sets up a simple scene. A chain falls onto a table. But the question it asks is where the paradox comes in. It wants us to prove that the force from the part of the chain that's still in the air and falling is somehow double the weight of the part that has already landed and is just sitting there. I mean, that just sounds wrong, doesn't it? It seems to completely go against our intuition.
And that's the central mystery we're going to crack today. Your first thought is probably, wait a minute, the only force is gravity, right? The force on the table should just be the weight of the pile of chain that's already there. How on earth can the act of more chain falling add double that weight and force? Where does this phantom force come from? Well, let's break it down.
Okay, so your first thought, and believe me, this is a very common trap that almost everyone falls into, is to just focus on the static weight. You see a pile of chain, you think, okay, the force is its weight. And that's a great starting point. But it's incomplete. It only looks at the static part of the problem and totally misses the crucial dynamic component, which is the continuous impact of those falling links.
So here's the absolute key to the whole thing. We're not just gently adding more and more mass to the pile. We are actively and pretty violently stopping a moving object. Every single link in that chain is falling, it's got velocity, it's got momentum, and the table has to exert a force to slam the brakes on and bring that momentum to zero instantly. That's where our extra force is coming from.
And this whole idea has a name, impulse. It's just a way of talking about a change in momentum. And here's the thing, you can't have a change in momentum without a force. Since the links are hitting one after another continuously, they create a constant impact force on the table.
Now this is really cool. We all learned Newton's second law as F equals ma, and that's fine for a lot of problems. But the deeper, more powerful way to think about it is that force is the rate of change of momentum, or F equals dp over dt. It's especially perfect for problems like this one, where the mass of the system we're looking at, in this case the pile on the table, is constantly changing.
Okay, enough talk. Let's get into the math and see how this actually builds up. We're going to calculate the two forces acting on the table separately. First, the simple static weight, and second, that all-important dynamic impact force. Before we start any physics problem, it's a great idea to define our terms. So, we'll call lambda the chain's mass per meter. We'll say x is the length of chain that's already piled up on the table at any given time. G is just gravity, of course, and v is the speed of a link right at that instant of impact. Getting this stuff straight now will make the math a whole lot easier to follow.
All right, step one. Let's calculate the force that you probably thought of right away, the boring old static weight of the chain that's just sitting there.
This is pretty straightforward. Weight is just mass times gravity. And since lambda is our mass per length, the mass of a length x is just lambda times x. So the static force, which we'll call W, is simply lambda x g. Easy enough. We'll call this our benchmark force. Okay, for the impact force, we're going to need to know how fast the links are actually moving when they hit the table. So that's our next step.
Now, since the chain is basically in free fall from rest, we can pull out one of those basic kinematic equations you probably remember from physics class. V squared equals 2 times acceleration times distance. For us, that's V squared equals 2gx. And you'll see in a second why leaving it as V squared is actually perfect for what we need next.
And now for the main event. Let's calculate the impact force using those momentum ideas we were just talking about. This is where the magic happens.
So remember, force is the rate that momentum changes. That means the impact force is the amount of momentum getting wiped out every second. Well, that's just the mass per second that's hitting the table, we call that dm dt, multiplied by the velocity v that it was carrying. Now, how much mass hits the table per second? Well, in a tiny bit of time, a length of chain equal to its velocity v hits the table. The mass of that little piece is its density, lambda, times its length, v. So the rate of mass hitting the table is just lambda times v. The full impact force, then, is that rate, lambda v, times the velocity v, which gives us lambda v squared.
Now for the payoff. We just substitute in that expression we found for v squared a moment ago. We know v squared is 2gx. So the impact force is lambda times 2gx. And just look at that. We have a nice, clean expression for the impact force, all in terms of x, the length of the chain on the table.
Okay, we did all the heavy lifting. We have our two forces. We have the static weight, W, and we have the dynamic impact force, F impact. Let's put them side by side and see what the physics is really telling us.
And there it is, clear as day. The pressure from the rested part, our good old weight W, is lambda gx. But the force from the falling part, that's 2 lambda gx. It's not just a little bigger, it is exactly double the static weight.
The math here is just undeniable. The force exerted by the falling part of the chain, the part that's actively getting stopped, is precisely twice the force of pressure from the part that's already just chilling on the table. The paradox is completely resolved.
So the answer was there all along, hiding in the physics of momentum. And here's a fun little extra thought for you. This means the total force on the table at any moment is the weight of the coiled part, which is W, plus the impact force, which is 2W. That means the total force is 3W. 3 times the weight of the chain that's already there. How cool is that?
So, what's the big lesson here? I mean, it's not just about a tricky problem with a chain. It's about a fundamental principle of mechanics. It's about learning to look beyond the obvious static forces to see the full dynamic picture.
The really crucial points to take away are these. First, force is fundamentally about changing momentum. Second, for any system where mass is flowing, like rain hitting a roof or fuel shooting out of a rocket, you absolutely must account for this dynamic force. And as we just saw, you can't ignore it. In fact, sometimes it's the biggest force in the whole problem.
This principle of momentum transfer is everywhere, far beyond this textbook problem. Think about a powerful fire hose hitting a wall, or the force of a hurricane's wind against a skyscraper. It's a really powerful tool for analyzing the real world. And that's our explainer on Irodov's falling chain paradox. Thanks for diving in with me.